All right. So, momentum. What's momentum?
It's the derivative of acceleration. Is that wrong?
So that the derivative of acceleration is called jerk. It's the rate of acceleration, which is like which you are familiar with. If somebody punches the gas pedal, they drive like a jerk, and you get pushed back really quickly, right? So it's not the derivative of acceleration. What does momentum mean? What does it mean, like, if we're doing some activity, people are like, oh, we got some momentum?
It's an inertial term. It's the amount of either movement or obstacles to movement that you get.
Okay. So it's about inertia, right? Something. Who else can tell me more about momentum?
It looks like a transfer of energy or a transfer of force.
Yeah. So momentum could be has to do with forces, right? And it can be transferred from one thing to another, or one thing having momentum can exert a force on something else.
I always think about potential. So if I've got some momentum, then I have some capital to spend later.
Mm-hmm. So you've got some energy already that could be expended somehow. So, yeah. So formally, momentum. So momentum is, I should just write is, not equals. Momentum is a mass m moving at a velocity v. So if you have mass and are moving, you have momentum. Okay? And so you can have momentum. You can be a really light object moving very quickly, and you can have the same amount of momentum as a very large object moving slowly. Because it's mass time, it ends up being mass times velocity. So momentum, we looked at some images. It can manifest in multiple directions. Doesn't have to just be one-dimensional. And what's that?
The integral of energy?
So it's related to energy. It's different than energy, right? So momentum. If we started from like a force equals a mass times an acceleration, right? And what do those little hats or little arrows I'm putting over those things mean?
They're vectors.
They're vectors, yeah? Okay, what does that mean?
There's directions in it?
There's a direction, right? So F equals ma. This is our Newton's second law, right? And we know that acceleration we could also express as the time rate of change of velocity. Right? So acceleration is how fast your velocity changes. So we could write it that way. Or we could even rearrange it just slightly and say that forces are equal to the time rate of change of momentum. Right? So what these bits that I'm putting green around right there, what this says is a force, F, will be exerted if there is a time rate of change of momentum. this right here, mass times a velocity, this directed velocity, this dimensional or has a direction velocity. This mv stuff, that is momentum. Okay? So mv, just to be really clear, that's momentum. I don't know why I abbreviated as mom. Add some levity maybe. So this is our key equation right here, right? If we change momentum, we generate a force. Or if we apply a force, we can change momentum. So, in the example of a baseball, when I hit the baseball with the bat, I'm applying a force to it. Right? I'm taking a bat and swinging it at a baseball. I am not changing the mass of that baseball. Right? That m is fixed. What I am doing is changing its velocity. I'm moving it into a different direction and probably accelerating it. Right? So this velocity change could be about a change in direction. So that baseball was heading in one direction and then it heads the other way. Or those two little cars that we bounced off of each other in the very first video. Right? You changed the direction that the slow-moving one was going. You bounced it back where it came from. So momentum transfer can be about a change in mass. It can be about a change in the direction of the velocity. Or it can be about a change in the actual velocity vector, or the actual magnitude of the velocity. Yeah? So you can change the m, you can change the magnitude of the v, you can change the direction of the v. Any of those three things generates a force, or is caused by a force. So this is the key, sort of the key concept for momentum. Let's see. Okay. Questions on this? Have people seen perhaps a pirate movie where a cannon gets fired? Right? So you fire this cannonball out of the cannon. And what happens to the cannon itself? It kind of kicks back. It wants to roll backwards, right? That's momentum. Right? In order to take that cannonball mass and accelerate it in one direction, there's this force produced in the other direction too, right? Like a reactive force, essentially. Right? That's momentum. Okay. So in order to generate, sort of what I'm saying is, in order to generate the forward momentum, right? In order to give that cannonball momentum this way, it generates this recoil force in the other direction, right? Okay, so this is conceptually momentum. Folks okay with that? Okay, so momentum derivation 2. All right. So, Reynolds transport theorem, derivation for conservation of momentum in one slide. Ready for this? So, our Reynolds transport theorem, you'll remember that we had to pick what is the thing that we're going to be interested in. And we called that thing B, right? That was kind of our placeholder back in Reynolds transport theorem. And in this case, it's going to be mass multiplied by that velocity vector. We want to keep track of momentum. And you'll also remember wherever there's a lowercase b, that was capital B per unit mass, or in this case, just a velocity vector. Because there's a mass dividing by a mass. So we can write the whole ugly thing out, okay? And again, I'm doing this to show you why we did Reynolds transport theorem and help you connect it. You'll never have to do this on your own. So if we plug this into our Reynolds transport theorem, this left-hand side integrated over the system equals, this first term is the accumulation of B within the control volume. So integral in the control volume, density V dV, and then there was a term that deals with fluxes across the control surface, right? So how much B, or momentum in this case, is coming and going. And this would turn into density times this velocity vector times V dot N times dA. Whew.
Matt, that's the derivative, that's the integral of the volume for the control volume.
This middle one here?
This second, yeah, the
Yeah,
V
this,
that's right after the
this
V.
middle term, that's a CV, right?
Well, it's the dB, that's a D volume, right?
Yes.
Okay.
Yes, correct. So this dV, let me just go over that in orange so people see where I did it. That's volume. Yeah, correct. Let me make that more explicit in my notes for next go. So this is your Reynolds transport theorem written out with these B's for momentum, right? And one thing you might already see, this first chunk right here, that is what we just defined as force on the previous slide, right? So all of that, we could write it as, and I'm going to write the sum of the forces just in case there's more than one of them, okay? So what I just did in green was take everything from the last slide. This chunk on the left is what we defined as momentum from our Newton's second law, right? Okay, so that's the setup, and that's big, ugly thing. So, time for the mathemagic part. Common things that we have done to make these problems tractable, at least for now. Steady flow, meaning dTs are 0. That should look and sound familiar. That's what we did for the energy equation. We're going to have a constant density, which means incompressible, right? So our density isn't going to change no matter what we do with momentum. And so this, this constant density, what that does is it lets you take these densities outside of these integrals. That's why that's a useful thing, okay? And just like we did for conservation of mass, we're always going to think about fluxes perpendicular to the control surface. Okay? And what that does is it deals with this term right here, this V dot N over in the right-hand side. Right? What that's telling you to do, that's saying I only want to deal with the velocity that's coming perpendicular. Right? You'll remember we did this with conservation of mass, and so we occasionally had to think about component vectors to get the perpendicular parts. We did a problem with like wind blowing into a garage that was set up that way, for example, where you had to deal with those components. All right, so we can go through, we can make these assumptions, right? And what you end up with is, and this is the equation that we're actually going to use in this class, so the sum of the forces in some direction equals the mass rate of the flow into or out of our control volume multiplied by the velocity out minus the velocity in. That's the equation that you should write down and put a box around and draw 3 stars and a smiley face. That's, or whatever your code is for this is important, okay? This is ultimately what conservation of momentum is going to boil down to for us, right? So just like the energy equation had this list of assumptions with it, we have basically the same assumptions that we've been making, right? And so this is actually part of what makes these things fit together, is that we're making similar assumptions. Just like we could also go back to conservation of mass and not, for example, we could have dealt with a spatially variable or a time variable density. You can also do that here. You can also do that in the energy equation. I'm showing you sort of the simplest form so we can get our head around how to approach these problems. All right, what are the things that people screw up on momentum? This is important, right? Because we don't want to screw up. So let's make the watch out list. All right. So, thing number 1 to watch out for. These little arrows over the top mean direction matters. Right? So, we're going to have to, in our problems, we're going to have to establish a coordinate system that says, for example, things moving to the right are moving in a positive direction, things moving to the left are moving in a negative direction. So you're going to have to establish a coordinate system that says which way is positive in one dimension and which way is negative. If you do not do that, you will get the problem wrong. So that's thing 1. Direction matters. Thing 2 is related. I'm just going to write the word minus. So these velocities have direction, right? Each of these V in and V out have a direction. No matter what their directions are, that's a minus sign. So if velocity in is moving in the negative direction, you would have minus a negative velocity, which will turn into a plus. Don't try and outsmart the math. Each velocity, you should always write it as having a plus or a minus and a magnitude. This equation, you should always write with a minus sign. Then you can be a smart enough person to say, minus a negative, that becomes a plus, right? Double negative. People forever are trying to put if this V in is negative, people are forever trying to then say, well, the negative's already there. There's already a minus sign. You will get the problem wrong. Or people are saying, oh, V in, that's in the positive direction, so this should be a plus. You will get the problem wrong. So write it with a minus, and then write each velocity with having a plus or minus, and always put this minus in the middle. And I'll show you that when we do the first example here. All right, thing 3 on the watch out list. Mass rate, okay? We've done mass rate before. It is a specific weight times a discharge, or a specific weight times a velocity times an area. Does that all look familiar? Maybe familiar-ish anyhow? This velocity that I just wrote in green pen in the bottom right does not have a direction. You can tell because it doesn't have a little arrow over the top of it. So if you're trying to figure out your mass rate using this approach that I've written in green, the velocity does not have a direction there. It's just the velocity through the pipe. It doesn't matter what direction it's going. Little hat, little arrow on top of me, direction matters. No little hat, direction does not matter. Yeah? Okay. These three pieces are the common reasons that people mess up momentum problems. Okay? So that's why I'm taking the time to point them out, because these are the super easy pitfalls. So I want to make sure we get in the habit of checking these when we work on a momentum problem.
Okay, so when we're doing a mass rate, Q is like Q in minus Q out, right? Like the mass rate would be the total change inside of your volume.
It's the volumetric flow rate across the control surface.
Across the whole, okay. Both are like.
It's not a net.
Surface.
Well, if you're at steady state, flow in has to equal flow out.
That's my, okay.
So that Q is representing all of the flow in or all of the flow out.
Okay, okay. So that's coming from like conservation of just how much mass is passing through at any given moment.
Yeah.
So you can use either velocity as long as you use the right area of the surface.
Correct. And we'll do an example on the next slide to help. I think this looks like it looks hard when it's Reynolds transport theorem style. Then it looks easy. Then I point out the things people do wrong and it looks hard again. So now let's do an example and get our heads around how this is actually going to work. Okay? So that's going to be our game plan. And